A rigid body has 6 degrees of freedom, so its equations of motion must be 6 in all. They can be put as the time derivatives of two vectors, the total momentum, which governs how the center of mass moves, and the total angular momentum, which governs how the body turns. The first equation comes from summing the momentum change over every particle. Total momentum is the total mass times the center of mass velocity, and its time derivative is the total force. Only external forces count. Internal ones cancel in equal and opposite pairs. In an external field, this force is the derivative of the potential energy with respect to the center of mass coordinates. Translate the whole body slightly, and every point shifts by the same amount. So the change in energy is minus the force dotted into that shift. The second equation gives the rate of change of the angular momentum. Work in a frame where the center of mass is momentarily at rest. Each position vector's derivative is parallel to the momentum, so that cross product drops out, leaving position crossed with force. Torque, like angular momentum, depends on where the origin is. Move the origin by some displacement, and every position vector loses that displacement. So the new torque is the original torque plus that displacement crossed into the total force. One special case follows at once. If the total force vanishes, the torque no longer depends on the choice of origin. The body is then acted on by a pair of equal and opposite forces. A couple does not push the center of mass. It only makes the body turn. The Lagrangian gives both equations directly. Differentiating it by the components of the angular velocity returns the angular momentum. Rotating the body through a small angle changes the energy by minus the torque dotted into that angle. So torque is minus its derivative. One more elegant result. Suppose the total force and the total torque are perpendicular. Then some displacement always makes the torque about the new origin vanish. The points that work form a whole line, and all the applied forces reduce to one force acting along it. A uniform field is exactly this case. Every particle feels a force proportional to the same constant vector, so the total force is the sum of the coefficients times that vector, and the total torque is one special position vector crossed into the total force. That position vector is simply the weighted average over the particles. In a uniform gravitational field, the coefficient is the mass, and the point is the center of mass, so the field reduces to one force applied there. Weight is a single arrow at the center of mass.